Welcome to Section 5, Lesson 12. Across the previous 11 lessons, we built every function concept. The rest of the algebra course depends on definition and vertical line test, function notation and evaluation, domain and range, linear functions, composition, inverse functions, piecewise functions, absolute value functions, transformations, even odd classification, and arithmetic combinations. Today is the marathon lesson where we apply all 11 skills back to back on a mixed sequence of challenges. Mixed practice is the most efficient learning move in all of mathematics because it forces you to first identify the type of problem and only then apply the relevant rules, which is exactly what tests, contests, and applied work demand. Section 5 closes with this marathon, and the next section opens with systems of equations. First idea on the board. Mixed practice exposes the soft spots in your skill set in a way that single topic drills never can. When every problem in a homework set is a domain problem, your reflexes carry you through. When the next problem might be a composition or an inverse or an even, odd classification or a transformation, you have to first decide which toolkit applies and only then start working. The decision step is exactly where weak students stumble and strong students breeze through. Today we exercise that decision step deliberately on a mixed sequence covering the full Section 5 scope. The full Section 5 toolkit has 11 skills, and you should be able to name them all from memory before starting the marathon. Function definition with the vertical line test, function notation and evaluation, domain and range identification, linear function recognition with constant rate of change, function composition with the inner-outer order, inverse functions with swap, and solve and one-to-one check, piecewise function evaluation with select, then apply absolute value functions in vertex form, function transformations with the 4 standard moves, even odd classification with the algebraic test, and arithmetic combinations with domain intersection plus 0, denominator restriction. 11 skills, all interconnected, all needed for the rest of the algebra course and into calculus. Third idea, speed and pattern recognition on mixed function problems come only from reps, never from reading the rules. The rules from Section 5 are short enough that 2 or 3 hours of careful reading covers everything. The fluency that lets you solve a mixed function problem in under a minute rather than 3 minutes comes from 60 or 80 practice problems spread across the next 3 weeks of homework. The marathon today is a starter set. Commit to working a similar mixed set on your own time over the rest of the chapter, and the Section 5 material will lock in as automatic background knowledge that the rest of the algebra course can build on without conscious effort. The full Section 5 toolkit has 11 skills, and a marathon-style mixed practice session is the most efficient way to lock them in as fluent reflexes. The first move on every mixed problem is to identify which skills the problem requires. Only after that identification do you apply the relevant rules. Today, we make the identification step explicit so you can train it deliberately rather than absorb it by accident. Skills 1 through 3 are the foundations. Function definition with the vertical line test for graphs and the no repeated input rule for ordered pairs. Function notation and evaluation with substitute and PEMDAS for any input. Domain and range identification using the no zero denominator and no negative radicand rules combined with graph or formula structure for the range. Skills 4 through 6 are the function family layer. Linear functions f equals mx plus b with constant rate of change as the defining feature. Function composition with the inner, then outer evaluation order and the non-commutative property in general. Inverse functions found by swap and solve with one-to-one verification by the horizontal line test. Skills 7 through 9 are the structural layer. Piecewise function evaluation with select, then apply on the right piece based on input conditions. Absolute value functions in vertex form, a times absolute value of x minus h plus k with V-shaped graphs. Function transformations applied through the general form a times f of b times the quantity x minus h plus k with the 4-parameter interpretation. Skills 10 and 11 are the symmetry and arithmetic layer. Even and odd function classification by the algebraic tests f of negative x equals plus or minus f of x. Arithmetic combinations f plus g, f minus g, f over g with domain intersection plus 0 denominator restriction for division. When you face a mixed problem, the workflow is read, identify, order, apply. Today's two worked examples each combine 3 or 4 skills with the identification step made explicit, so you can practice the decision-making layer rather than just the mechanics. Here is the first marathon problem. Given f of x equals 2x plus 1 and g of x equals the square root of x minus 3, compute the symbolic rule for f composed with g, identify the domain of the composition, and determine whether the composition is even, odd, or neither. The problem combines composition, domain analysis, and even, odd classification. Step 1. Identify the skills required. Composition for the symbolic rule, domain analysis for the second part, even, odd test for the third part. 3 skills layered into one problem with the composition feeding into the domain analysis and the resulting function being tested for symmetry. Step 2. Compute the composition rule. F composed with g of x equals f of g of x equals f of the square root of x minus 3 equals 2 times the square root of x minus 3 plus 1. So the composition is 2 times the square root of x minus 3 plus 1. Step 3. Identify the domain. The composition is defined where the inner function g is defined, namely x is greater than or equal to 3, so the radicand is non-negative. After applying g and getting a non-negative number, the outer function f accepts any input, so no further restriction. The domain of the composition is from 3 to positive infinity inclusive. Step 4. Test the composition for even odd symmetry. Compute the composition at negative x 2 times the square root of negative x minus 3 plus 1. The radicand is negative whenever x is positive and negative for x less than 0, so the function is not defined for any input outside the original domain. Specifically, the function value at negative x is not even defined when x is positive, so the symmetry test cannot run cleanly. Functions defined only on a half line cannot be even or odd in the usual sense because the symmetric inputs are outside the domain. Conclude the function is neither even nor odd because the domain is not symmetric. Step 5. Sanity check. The graph of 2 times square root of x minus 3 plus 1 is a half parabola starting at the point 3, 1 and curving upward to the right. The graph has no symmetry across the y-axis or the origin because it does not extend to the left half of the plane, consistent with the neither classification. So the composition is 2 times square root of x minus 3 plus 1 with domain from 3 to infinity, and the function is neither even nor odd. The big lesson from this example is the layered skill workflow on a problem that touches 3 sections, 5 skills. Composition produces a new function. Domain analysis identifies the input range. Symmetry test fails because the domain is not symmetric, an important edge case. Always check that the domain is symmetric across 0 before applying the even-odd test, because the test is meaningless on asymmetric domains. Here is the second marathon problem. Given f of x equals 2x plus 3 and g of x equals x squared, find the inverse of f, compute the arithmetic combination f plus g, and identify the resulting domain. The problem combines inverse functions and arithmetic combinations. Step 1. Identify the skills required. Inverse function for f, arithmetic combination for f plus g, domain analysis for the combination. 3 skills working on f and g separately and together. Step 2. Find the inverse of f using swap and solve. Write y equals 2x plus 3. Swaps and yx equals 2y plus 3. Solve for I, subtract 3 to get x minus 3 equals 2y. Divide by 2 to get y equals the quantity x minus 3 over 2. So f to the negative 1 of x equals x minus 3 over 2. Step 3. Verify the inverse by composition. F inverse of x equals 2 times the quantity x minus 3 over 2 plus 3 equals x minus 3 plus 3 equals x. Identity verified, so the inverse is correct. Step 4. Compute the arithmetic combination f plus g. F plus g of x equals f of x plus g of x 2x plus 3 plus x squared. Rearrange to standard polynomial form x squared plus 2x plus 3. The combination is a quadratic polynomial. Step 5. Identify the domain of f plus g. Both f and g are polynomials defined for all real numbers, so the intersection of their domains is also all real numbers. No additional restriction applies because the combination is addition, not division. The domain of f plus g is all real numbers. Step 6. Spot check at x equals 2, f of 2 equals 7, g of 2 equals 4, f plus g of 2 equals 11. Symbolic check 2 squared plus 2 times 2 plus 3 equals 4 plus 4 plus 3 equals 11. Match. So f inverse of x equals x minus 3 over 2, f plus g of x equals x squared plus 2x plus 3 with domain all real numbers. The big lesson from this example is the parallel application of two different function operations to the same pair of functions. The inverse of f acts on f alone. The arithmetic combination acts on both f and g together. Each operation has its own procedure and its own domain rules, and recognizing which is being asked is the central craft skill of mixed function problems. Section 5 problems often combine 2 or 3 operations on multiple functions, and the mixed practice format trains you to keep them straight. 3 mistakes that catch every algebra student during their first weeks of Section 5 marathon practice. Each one is fixable by a small explicit habit applied between problems and at the end of every problem. First mistake: applying the wrong skill first because you misread the problem type. A student sees a problem that asks for the inverse and immediately applies the swap and solve procedure without first checking whether the function is 1-to-1. If the function fails the horizontal line test, the inverse does not exist as a function, and the swap and solve produces a meaningless or partial result. The cure is the explicit identification and diagnostic step at the top of every workflow. Read the problem, identify the required skills, run any relevant diagnostics like 1-to-1 verification or domain symmetry check, then apply the operations. Second mistake: confusing function multiplication with function composition due to similar looking notation. A student looking at fg of x or just f of g of x without the small circle interprets the notation as multiplication when the surrounding problem context indicates composition, or vice versa. The notation is technically ambiguous in some textbooks, but the convention is small circle f circle g means composition, juxtaposition fg or explicit times symbol means multiplication. Read the problem context carefully and apply the correct operation. Third mistake: running the even-odd algebraic test on a function whose domain is not symmetric across 0. A student looking at f of x equals square root of x tries to compute f of negative x, finds the radicand becomes negative, and concludes the function is not even or odd because the test fails. The correct conclusion is that the test is meaningless on an asymmetric domain like x at least 0, and the function is therefore neither even nor odd in the strict sense. The fix is to always check that the domain is symmetric across 0 before applying the even-odd test, and to immediately classify functions on asymmetric domains as neither without running the algebraic test. Mixed function skill marathons are the dominant form of math evaluation across standardized tests, calculus prerequisites, and applied modeling work. Specialized single skill practice builds individual fluency, but mixed marathons build the decision-making fluency that real applications demand. 4 broad domains below. On the S8 ACT, GRE, and most state algebra exams, function items routinely combine 2 to 4 Section 5 skills in a single problem: definition plus domain, composition plus inverse, transformation plus even-odd, arithmetic combination plus domain analysis. Test writers know that mixed practice is the gold standard of fluency assessment, so they test in exactly that style. Students who have done 60 or 80 mixed function marathon problems before the test consistently outscore students who only did single topic drills. Section 5 is the prerequisite gateway for calculus, where every concept builds on the function machinery covered here. Limits use function evaluation and domain reasoning. Derivatives use the chain rule from composition and the difference quotient from linear functions. Integrals use even-odd symmetry shortcuts. Inverse functions appear throughout. Mastering the Section 5 marathon skills now means calculus next year will be conceptually easier because the function fluency is already in place. In programming, function design uses composition inversion and arithmetic combination patterns extensively. Functional programming languages use composition as a first-class operation. Many libraries offer inverse functions for transformations like rotations and color conversions. Aggregation operations like map reduce combined functions arithmetically. The mathematical concepts you build today translate directly into software engineering practice, with the same mental moves being relevant in both contexts. In engineering modeling, complex systems are decomposed into component functions and recombined through composition and arithmetic to produce overall system models. Filter chains in signal processing, control loops in robotics, multi-stage manufacturing models, and many other applied scenarios rely on the same toolkit you built across Section 5. Engineering analysis at the conceptual level is essentially function analysis applied to specific physical or digital systems, and the Section 5 skills are foundational across the entire engineering curriculum. 3 things to take with you from this marathon lesson today. Mixed function skill practice is the most efficient learning move once the individual skills are at least passable, and the Section 5 toolkit is now complete enough to support marathon-style practice for the rest of the algebra course and into calculus. First, the 11 Section 5 skills cover the complete function fluency needed for the rest of the algebra course: function definition, with the vertical line test, notation and evaluation, domain and range, linear functions, composition, inverse, piecewise absolute value, transformations, even-odd classification, and arithmetic combinations. Every problem in the rest of the course exercises some subset of these 11, and recognizing the relevant subset is the first move on every problem. Second, the first step on every mixed function problem is to identify which of the 11 skills apply, in what order. Read the problem completely, name the skills required and their order, run any necessary diagnostics first, then apply the operations. The identification step takes 10 to 20 seconds and prevents the wrong skill first error that wastes minutes on every problem it occurs in. Always run the appropriate diagnostics before applying the main operation. For inverse, verify 1 to 1 with the horizontal line test or the strictly monotonic argument. For even odd, verify the domain is symmetric across 0. For composition, identify the inner and outer functions before evaluating. For arithmetic combinations, identify any domain restrictions, including the zero denominator rule for division. The diagnostics take 10 seconds each and prevent silent errors that lead to wrong final answers. Coming up next, Section 6 opens with systems of linear equations, where 2 or more linear equations are solved together to find a single unique solution that satisfies all of them simultaneously. Systems of equations are the natural geometric extension of the linear equation solving from Section 3 and the linear graphing from Section 4, combined into a single more powerful tool.